They do work on the board. The eraser is so saturated with stuff. It really just ruins it.
My high school didn't have after whiteboards. The income place, and they had shower wall. I didn't think that they do file. You could write on it, but it did not erase. So the only way to erase stuff on it was with like this is for talking about.
You in the West?
Yeah.
You took her.
I did. And I got to make some skip days. One of the by sunrise, 6:30 Saturday. Yeah, I'm a copy film in October. So if you do it during the summer, yes, but if you do it after October 2nd, that's not going to do it. That's what the people are helping, like May, October. That's what you need in the water. Yeah, they forcers takes down the table. Do like all those seconds. You can sir. That's good. I don't even want to do the killer. The killer, I feel like I suicide, and I'm straight up the base. I could use this regular too. Where we're going to camp, right? Yeah, I can still into the face. Yeah, they hated start hiking at 4:30. Yeah, that's why I want to go. It's 6 miles.
We only offer around 400.
Exactly, yeah. It's like another 4 miles. Yeah. Great. Yeah. Walk down the other side of the mountain, got over here, use the car, drive down home, and 3 days. And it was all over. And everyone laughed. Do homework all day Sunday.
Yeah.
Work on PE studying all day Sunday.
Wait. Oh,
Yeah, just say if you save it all for the last night, I can save one night, yeah. I should do that more often. We're like, it's
What's that?
yes, like a root.
It depends on.
Absolutely bomb. Get some baby there.
I ain't not there.
Oh, God.
So it wasn't gone through.
Bike
the
good?
All right. Let's go ahead and get started. Still catching up on grading homework, but you guys should have 2 back now. And before we move on, let's talk just about a few nuances in 2, because they come up again this week. There's kind of an oddity. We made that doublet by taking source sink inside of a uniform flow, and we brought them together so they were exactly on top of each other with some trickery on mathematics. so that they didn't completely just wipe each other out. And the end result of all three of those was getting a streamline that was a circle. And I don't, this might have been the first time I saw it. One person, the equation you get out has a minus sign in front of it after you do all that math. Somebody had left the minus sign off, which is like putting the sink here, source here. And you wouldn't think it would make any difference because you bring them to the point where they're on top of each other. But as it turns out, it does. If you do this with this, you don't get the circular streamline. You end up getting, well, it looks like a venturi actually. Kind of sucks stuff in. Anyway, it's kind of weird. So it does matter. And if you take this away, what do you get by the time you collapse them to a doublet? You don't get, you don't get anything really. I mean, technically any streamline can be a body, but you don't get anything circular. You end up getting these kind of magnetic field lines that go out to infinity. It's a self-similar problem, so no matter what scale you look at it, it's the same. Oddly, there's another way to get a doublet, which don't usually do in here, but if you take a vortex, another vortex, and you bring those together, let's restrain them this way, and you'll also get a doublet that's equivalent to the source and the sink together. There, if you remember, the velocity fields were orthogonal to each other, so ends up working out the same. Another thing that came up in the homeworks, which I don't think I took any points off for, but when people are getting creative with their own things, we had a number of people who tried to make like a doublet out here with or without a vortex, and another one here without a vortex, hoping to get 2 cylinders. The thing about potential flow is that any singularity anywhere affects the flow everywhere. So the fact that this one exists messes with the shape of this one. By the time you drag them apart to infinity, okay, you'll get 2 cylinders that are rotating, but when they're close to each other, you don't. They actually affect each other, so they're going to deform the shape in some way. Probably you'll still get a closed contour, but I don't know if it's guaranteed. I think if you don't have the vorticity, for sure you will. But if you have the vorticity, I don't know if you could prove that you would always get it. So anyway, it's a little odd. If you actually want to get a specific shape, we used to do a panel code you guys had access to. People played with it. You're supposed to play with it for homework 3, but I haven't looked at those yet. There we actually have a specific shape, right? Just like a NACA 2412 or whatever else you want. And if you're trying to do the ground effect case, where you have image airfoil down below to make it like it's near a ground plane. If you try to do this with a whole bunch of sources and sinks, like camber line or something, you might be able to get it to work, but you'd actually have to move their positions as well because of the corruption of the image one. So the panel method is actually the only way to go. Literally have your sources and sinks on the surface, your control points on the surface. No matter what you do here, it's going to maintain that shape there. Anyway, nuances of potential flow. We're going to actually do a little more with potential flow this week, following some of Platzer's work in chapter 5. So we want to get on to cylinder bodies now. So we've been looking at all these 2D things, which are nice. You can solve those pretty easily, either analytically or potential flow, CFX, whatever. Now we want to start looking at slightly 3D things. So let's imagine a wing that's cylinder. kind of like a aerial star cruiser or something. So we have our one of these. Show up. X-axis, y-axis, Z's out of the board, and so the span B is a function of X. Back, big B, and then here this is root chord length. I'll assume it's like a delta wing, so tapers nothing at the tip. And let's give it some thickness. So let's keep it nice and symmetric. Say it's sort of a diamond profile. Z direction, Y direction. And so we want to figure out how to analyze what's going on in there. We're going to go back to the linear theory of perturbation theory. Some potential flow thrown in. For the moment, let's say that it's incompressible. Later we'll change that. Let's say it's inviscid. Keep that. The inviscid is so that we can apply a tangency tension to the wall, which is sort of a requirement of perturbation theory. But otherwise. Okay, so and let's say that alpha equals 0. There's no lift. So we want to use potential flow to do this. If it doesn't have any lift, we don't need any vorticity. So we can create this 3D volume if we're crafty by using a bunch of distributed sources. So let's say that inside basically the Z equals 0 plane, so the planform area of this thing, this triangle, we're just going to distribute a whole bunch of sources. The limit will make it infinite. And what we want to do is come up with a way to define what strength each of those has to be based on its location in order to create a stream surface that has this 3D shape. Okay, so we have been dealing with potential flow in 2D, and now we want to move to 3D. And we're going to treat these as sources. So in 3D, it's almost the same. ER is going to be some strength over, and if you remember in 2D, it was over 2 pi r, right? Because it was a slice, it's uniform, so we had to distribute some mass flow rate through some area of squishing through. So same thing here, the area now, because it's spherical, is the area of the sphere, is 4 pi squared. And then we still have that VR is equal to EDR. So solving for lambda, get 4 r squared EDR. And we can integrate that. E minus lambda over 4 pi r. All right, so that's the potential for one source. So we now want to distribute them. So we need a way to kind of index everything. So let's say that phi, the value of phi at some random point x, y, z, some point out here, y, z. We want to solve for phi there. So it's going to be equal to minus lambda over 4 pi r. But r is the distance. Let's say this is my particular source. So it's that r. So for r going to be square root of x minus c squared plus y minus beta plus b squared. So that's the zero offset, the origin. Said everything's, all the sources are going to be on the z equals 0 planes. Offset for z. All right, so source is located at point C8 theta, and the point we're solving for find p values of x, y, z. All right, so plugging that stuff in, you get minus 1 over 4 pi. Oh, that's for a single source. So now we need to essentially sum them all up. So you could do like a double sum if it was numerical. But we're actually going to assume it's continuous. So we'll get a double integral. Lambda c theta over r theta. So with that, we could solve for p anywhere, assuming that we know this. We need a boundary condition to drive that. So that boundary condition is going to be, whoa, tangency. We have to somehow creatively come up with a way to solve for that. Make sure that we have streamlines that are parallel to that surface area. All right, so we're going to go back and use same approach we had with perturbation theory in the last chapter. So we're going to sort of ignore the z deformation of the body, but we're going to keep the slope because that slope is what introduces a perturbation velocity in the z direction. So our w velocity, the perturbation velocity, w x y 0. Technically, there is a z displacement. In perturbation theory, we skip it, so we're still saying we're on that plane, but there's a velocity that's induced by the slope, just like we had before. It's going to be our free stream speed. Y just hdx. We don't care about the slope in the y direction. Okay. Good. So we have these individual sources that all have strength lambda, and you can assume that half of the m dot basically that comes from each one of these, half goes below the z equals 0 surface and half goes above. So we can come up with a there. We have lambda c and theta be 2 times w c theta 0 plus. For the plus side, just worry about 1/2 and then double it. Good to go. And we can plug in our w as that 2 u theta. All right. So presumably you know the shape of the body. So h of x and y known. We drew it as a simple diamond shape, but it doesn't have to be. It could be something arbitrary, as long as you know what it is. If you know that, you also know h prime. So in principle, you could take that, throw it in here. If you know that function, probably just perform the integration. It's something you could do in closed form, or numerically you could do it some other way. But that's not interesting for our particular analysis. So instead, we're going to keep manipulating this thing. Yeah, we can just take that and plug it in. Then 2u comes outside, so we get a 2u. This so h prime. That's why. Yeah. And this R, we left it. It's this big thing, but if this body is slender, certainly it affects flow nearby. But from potential flow, as we just discussed, a disturbance anywhere affects the flow everywhere. So if I go really far away to point XYZ way out here, there's still some disturbance. And if you look at R, the R in here, if I move really far in the span-wise direction, then eta is actually contained inside the planetary area of the body, but Y can be huge. So eta might become super small compared to Y. And so what we can do is we can split this problem up. Instead of one comprehensive integral, we can instead consider sort of a near field region and then a far field region and analyze the two separately. We want to split that up. It's here. So we can rewrite that. Let's pull this for the constants to the other side. So we get 2 pi u v z. And that's equal to minus integral h prime c of theta over, now instead of r, we're going to have x minus c squared, y squared, theta. This is the far field. Well, we've assumed that eta was small enough we can neglect it. But we can't just do that. Can't just throw away the other terms. So we got to bring them back in. So we get minus double integral h prime of c and theta. And then we get 1 over r. That was our original equation, right? Was the h prime over r. And then we have to add this one back in basically. So minus 1 over this thing minus c squared plus y squared. Just doesn't look like it helps very much. Nothing. Near field. All right, same equation. We just broke it up.
No. No.
You try to say something? All right, so if we look at the far field part, the denominator is no longer a function of eta, so we don't have to worry about that. We can easily integrate it. And let's see. The rest of it comes in area integral. So integrating the C part finds something called Q of X, conceptual area. It's integral to 2 times integral from minus B of X over 2 to B of X over 2 of H X and Y. That's really just integrating that chunk. And the 2 gives you the other side. Oh, sorry, the 2 gives you the Z side. That's just cross-sectional area. So we take the derivative with respect to X of that. Move X, X. And that'll be equal to 2 times the integral minus B of X. B of X over 2 of H time of X, Y, Y. And now I can take that and plug it into here for our far field component. We'll get the far field. It's 2 pi over U E of X Y E minus a half integral from 0 to C Q time of C over root X greater plus plus squared. So C is it's in the X direction, right? It's if we integrate from the nose to the tail. Yeah, so this whole thing is only a function of X. This is the rate of change. And then the rest is just how far away you are from a singularity. What this really means is that this component, we only really care about how cross-sectional area changes as you move from the nose to the tail. We couldn't care less what the shape is. So we drew it as this kind of slender diamond, but it could be a body of revolution, be something else. As long as Q prime of C is the same, then the far field behavior is the same in terms of basically they're shoving flow out of the way. It turns out when you get very far away, the shape no longer matters. That's kind of the first hint of this whole deal of area.
What do Eta and
They're
do they like represent me physically, or are they
so they're X and Y coordinates, but they're X and Y coordinates of a particular singularity. So speak C eta of that particular source. So you can think, in fact, the nodes actually interchange X and C and Y and eta quite a bit. X, Y, and Z here are where you're trying to determine a phi value, but it's from the potential flow that's created at, in this case, X equals C. I don't know if that helps or not. Uh, I mean, it's a little like homework 2. 3D makes it a little messier, but you always place singularities at various XY coordinates. The offset was handled by this, we would call this X minus X naught, probably the way we did it in 2D. That was Y minus Y naught. Here, for some reason, he chooses C and eta, but it's the same idea. Yeah.
What is the Y minus?
Oh, so this is the far field bit. Sorry, I just erased the split integral. We took the full phi and we split it into a near field part and a far field part. So this is the far field part. And the reason we did that is said we'll apply this equation only when we're far enough away that eta y minus eta became insignificant.
Okay.
There is another piece to the equation that we're going to have to throw back in. That's the near field part. The far field part, though, the kind of the takeaway from this, hopefully we'll less a little bit later, is that if this is a contributor to, say, drag on the vehicle, that all you really need to know is this area distribution. You don't have to know specifics about the particular shape. Let's see. So now we do need to bring in the other bits. So if we bring the near field part back in, towards. So if we combine the near field and the far field, get the x, y, v is equal to u over pi integral minus b of x over 2 x 2 of h prime. There's another one now. Get you. It's the x that we're located at, but eta where the singularity is. Natural log y minus eta squared z squared the eta plus big P P at big PSP. Much other junk in it. Right, minus u over 4 pi integral 0 to c or u prime of c over root x minus c squared plus y squared c minus big U over 2 pi U prime of log pi squared. So this part they call the cross flow potential. And the rest is the spatial. The idea behind this is that as essentially this thing gets shoved through the flow, it's creating a flow inside of a plane. It's shoving particles away from the body, the center axis. So all of that's contained in here. And then everything else goes out here. This one is sectional. This everything except the DSP. It's at a given cross section. X only shows up here as part of the slope of the body. Everything else is just essentially the area integral. This one brings in stuff from upstream and downstream. But this only depends really on this area distribution again. So Q is a function of X. It really matters. So we start to use this to analyze wave drag. If it's incompressible, there is no drag. It's all based on potential flow. There cannot be any drag. But we can actually come up with a compressible form of it. We want to write it, but the SP for the compressible part is U over 2 pi prime of X, natural log of beta over 2X minus integral 0 to X Q prime of C to prime of X over X minus C C for beta I is squared. Here, the compressibility doesn't actually show up. We'll see this again in the next part, but I think the gist of it is that the velocities are induced by a slender body pushing stuff out in the crossflow. What you're basically looking at, here's my diamond cross section. And as it's coming forward, it's inducing a velocity outward. And that little perturbation velocity, even if we have a supersonic flow coming in, this is very subsonic. In fact, it's subsonic enough that you can ignore the compressibility aspect of it. It's okay. You can actually, we'll do this in the next couple of assignments in CFX. You can plot this in CFX for some of these shapes. See if that's actually not a bad problem if the body is slender. Okay. This was for compressible. And the end result is that the wave drag, at least from this perturbation theory, wave drag comes pretty much entirely from this rate of change of cross-sectional area of the body. So it's kind of getting back to some of the discussions we had about supersonic aircraft design, not allowing this to change super abruptly. If it turns out that drag is pretty much dominated by this area changing, then you might imagine that people would be interested in determining what the best shapes are. And so there were actually some studies on this. Carmen came up with one for bodies that blunt back in. Carmen, he did bodies of revolution that blunt at the back and found optimal shapes. And then was it Hack and Sears? Ones that were essentially pointing at both ends. Anyway, they came up with analytical analysis that determines what are the best body shapes for minimizing drag. As it turns out, again, because things are only a function of cross-sectional area, they did bodies of revolution because it was easy to analyze. but you don't have to. You could turn these into things that are fatter in one direction or the other. And because that doesn't affect keep effects, you still get the same drag. Turns out even if you disturb it a little bit, the effects aren't too brutal. This whole concept of area ruling kind of became, I guess, known in about 1952 by this guy called Oswitich, Austrian, who was Platzer's advisor for his PhD. And then Sears was my advisor's advisor. So anyway, all this stuff comes kind of full circle. So Oswitich did it in Austria, and then there was a guy in the US, Whitcomb, that did it, I think, also in 1952, but it was a classified report that didn't get released until 56. Same thing. This is all area ruling. And then I don't know where he found it, but somehow Platzer dug up a patent that was filed in 1944 in Germany that covered the same thing, but of course, nobody knew about it for quite some time through the fog of war. Okay. So anyway, that's kind of the background behind area ruling. And like I said, you see it in every supersonic aircraft that you find now. If you ignore it, you pay later. So the F-18 Super Hornet, I think, is a good example there, but there's some pretty well-designed airplanes that make use of that. All right, all of that was non-lifting aircraft. So now let's consider throwing in some lift. And it might initially seem super hard. Used to having to throw in vorticity. So it seems like we might have to repeat that whole thing with vortices added. Turns out we don't. There's another approach you can take for this. So let's imagine that I've got some, let's say, the body of revolution. It's easy to draw. And it's traveling some speed. It's got a body axis, X, R, revolution. And it's at some angle of attack here. And it's got outer radius. It's a function of X. So we want to figure out how to analyze that. And it turns out there's a completely different way we can do this that it's a little more straightforward. So let's imagine that we've got some cross section here, orthogonal to the flow. And this thing over time is going to like just drive through that cross section. So let's look at what happens to basically the intersection of the body with this cross section over time. So right as it hits, right as it hits, there's going to be a little circle that's basically at the origin right as it goes through. But you can see as it goes through, the intersection of the x-axis with this vertical plane is going to move down, right? So this basically this little circle is going to be moving down with some delta. And then it's going to change size. So if we go to a later time, the axis be down here. Center, it's growing because of here part of the diameter is intersecting. Some later time, bigger. And so what we want to do is we want to think about what this is doing to the flow. So there's two things. It has to, it's shoving the flow out of the way, but at the same time, it's moving downward through that cross section. So the principle here is called added mass. I don't know, has anyone, you guys had to deal with added mass before? What was that? one of my early CFD problems as well. Learning how to use running peta, I guess. If you try to compute the trajectory of, say, somebody throwing a baseball, they launch it with some initial speed, some angle, and then you just use essentially kinematics. You know, a CD for a sphere, and so you just apply CD and you integrate over time and try to predict its trajectory, what the range is going to be. It turns out if you use just CD times surface area and integrate the velocity, you completely miss, you overshoot by quite a ways what the ball's actually getting. It would work great if this was in a vacuum, but it doesn't work well. It wouldn't work great in a vacuum either because CD would go away. It turns out, so all of our equations that we use for all of physics and aero, it's usually Newton's second law, right? F equals ma. So we're used to thinking about ma for ball because it's relatively heavy. The trouble is the act of the ball going through the flow and taking flow and shoving it in to fill up the gap behind it. And there's an ma associated with that. So they call that added mass. It's as if the ball weighs more than it actually does. And it's because of the extra mass of the fluid that it has to shove out of the way. In air, usually it's not huge. The air you get isn't tremendous, but it's there. Go into something heavier like water, and if you ignore added mass, you get punished pretty badly. So anyway, that's really what we're trying to analyze. This thing is kind of like a cylinder that's moving down. And if we treat the added mass from the fluid that gets displaced and has to fill in the gap on top, that's now becomes the lift picture out of this thing. I don't know if that makes any sense, but so there's two components of the velocity. There's going to be one that's just because it looks like the cross-sectional area is growing, and the other is that the whole thing is moving. Now the bit that's when we look at these cross sections, this cross section is moving down, so it's kind of like a cylinder that sees flow coming up, right? And so we might use what we know about 2D potential theory to imitate this. So I would maybe think about using what in here? So a doublet. You have to be a little bit careful because our velocity is now in this direction. So I would have wanted to make the doublet by having a source and a sink come together. They have to be aligned with the flow. So we'll just have to make sure we rotate the axis of what's we have as Z here used to be our X. Okay. Let's see. And again, even if we're treating this in supersonic flow, even if this is greater than 1, the component of the velocity that's stuck inside this cross-sectional area is likely to be quite small. In particular, if you can consider this to be a slender body. And so we can get away with ignoring compressibility in this particular case. So let's start some numbers up. All right, so our cross-flow analysis, we use our 2D doublet, incompressible flow, rotating it so that the flow direction is in the Z direction. So we'll have P of X, Y, Z of our doublet equal to mu of X, where mu is the strength of the doublet. over 2 pi d over y squared plus z squared. That should look about like what we had for the other thing. I think they used for a term here in the book. I think there was a minus and then the x, y, and z's are shuffled. If we want to go to a cylindrical coordinate system, e of x or z u of x 2 pi c over squared d squared. And oh yeah, that's just subbing in r, and then in cylindrical coordinates, e of x or theta is equal to minus u of x 2 pi r times theta. We're in our cross section here. Got r. And our velocity is coming up here. It's axis x. So basically, how quickly the axis drifts down, velocity goes the other direction. All right. Let's see. Theta. All right. So now what we need to do is find u of x or tangency. And we have two contributing things, right? This is the doublet. And then we also have a free stream component. We need to add in that VR free stream is WA of x times cos theta. And then VR for our doublet. Equal to EDR this, which is minus u of x for 2 pi r squared cos theta. And okay, so we need these two to cancel each other out when we're on the surface. Little r, right? Little r is anywhere, right? It's in position here, but from our axis up to the surface is always the big R. All right, let's take a bio break.
Oh, yeah, whatever. Dude. I guess. You might have to- Right in there. They seem like a great list there. Happening now, man. Right now. Right, you can still be here. Like small, I mean, on ours, it was like.
I think we're all here. Go ahead and get started. So the reason we like to shove this into the cylindrical coordinate system, our coordinates, well, so the body's moving, which gives us our free stream flow hitting the doublet, which creates the cylinder. And if you remember well, we didn't actually go through that derivation, but the reason you discover that there's a circular streamline is you search the flow for places where PR equals 0 and end up with an equation for the radius of the cylinder. So we're going to do kind of the same thing here. So we have our free stream, we have the equation for the doublet, and at the surface, dr is going to be equal to 0. So if I set these two equal to each other and then solve for the case where we're at big R, then we can get our final equation. So summing those up, u of x over one e of r, r equal to r of x, is equal to minus u of x over 2 pi r squared theta. And then we're going to set that equal to the free stream speed, equal to really plus of x cos theta 0. And then so the cosines cancel, and we can solve for u of x. 2 pi big R of x squared times a of x. So now we can take that and we can plug it back into here. minus the r of x squared WA of x cosine theta over r. Okay. So we can now use this to find the lift per section per dx. And so we can get an equation for that. Which is equal to the integral around the perimeter pressure times cosine theta dl, where dl is going to be cosine theta is to get the lift component, the vertical component. And rewrite that as time integral 0 to 2 pi from the circumference of the circle. And we can go ahead and subtract a p infinity from this, because if I had a p infinity, it's not a function of L or theta, so it would go away anyway. We get p minus p infinity. Oh. And remember that P is P minus P infinity half rho U infinity squared. So I can take that and shove it into here. We'll get a rho U. Yeah. Back right. Half. So infinity squared integral 0 to 2 pi P of x r of x cosine theta. Okay, and then let's take our linearized approach for CP from the last chapter. So we had CP was what, minus 2 over U. That's incidentally, how many people have for homework 5? How many people started to get results? I know you have. Anybody? Couple. Anybody done the comparison with CP, the perturbation theory yet? So questions always come up on how accurate you should assume that should be. And so what you might want to do is do a couple of simple cases where you analytically solve for this for different. This ended up being theta. I guess it was minus 2 theta over beta for the compressible case. So plugins, a couple of numbers here, and then go into the VT compressible calculator for both compressions and expansions. Just try a couple, and you'll get an idea of how big a deflection can be before you don't want to use that method anymore. Generally speaking, that kind of perturbation theory, it's like first order estimate at best, so don't expect anything super precise out of it. Okay. So if we plug that in, and then also our fee, and we get CP, C and CP. CP for our little r equals big R. To not do the CP is minus 2 over u ddx. Now we sub in our phi minus big R x squared WA of x cosine theta over little r. And then on the body, that's where little r equals big R. But little r for a cross section is y squared plus b squared. So it's not actually a function of x. So we can actually yank the little r outside of the ddx. But then we're going to solve for it at big R. So CP of little r equals big R, the minus, sorry, the minuses go away, get 2 cosine theta over u big R of x, dx squared of x, and then that we want to plug into the lift interval. Finally, we get a lift integral function of x. That's going to be rho infinity u big R squared x WA of x integral from 0 to 2 pi cosine squared theta theta. That goes to pi. Finally, we get rho infinity u dx big R squared pi. Okay, and so now you mentioned we were going to use this added mass principle. So if we start by looking at the mass of the air that's displaced by the little slice of body that's going through that cut plane, we can define a little of x. But this is the mass per length. So it's a slice in the YZ plane for a given x. So it's going to be just rho times pi r squared. Right. Area times density, mass per unit length. So we can now take that and plug it in. We've got the r squared, the pi, rho. So we're left with u times dx Bags. I guess I call this the convection. So we need to maybe consider a couple of possibilities here. We've got this missile-like shape, some angle of attack traveling through the flow. And it's got some angle of attack. The angle of attack could be steady or it could be unsteady. If it's steady or constant, then we just get W equals U minus alpha. If it's unsteady, then we get alpha x and now time be something like ddt plus u dx times r x, I guess. If you could rewrite that as d dt. And this looks a lot like our momentum equation, where this would be equal to sum of the forces. I have people in A. So that's kind of where this all comes from. Lift is equal to time rate of change of. Even in the steady case, because our cross-sectional area is moving, we end up getting that lift. Okay, so the missile's imparting momentum to the flow and it gets lift from it. So we have our equation for a sliver. To get the total lift, we now need to integrate that from the nose to the tail. So the total lift is going to be the integral over the body. So prime of x is x, which is pi rho u, integral from the nose, tail, dx r squared x ua x dx. And if alpha is constant, then WA of x just becomes U alpha. U alpha for alpha. And so we can yank it outside. So finally we get that it's pi rho u squared alpha minus r squared tail minus r squared nose. Which is keep it simple. Still got a couple of options. We could have a pointy nose, so that goes away, and a blunt tail, and so then our lift is that. If we have a pointy nose and tail, what happens? There's no lift. Yeah, so anyway, from linear theory, that's the gist of it. If the nose and the tail are the same, the slender body contributes nothing to lift. I haven't actually tried to see how far you can stretch that in terms of moving away from perturbation get it to work out, but I guess you could try some simple stuff in CFX. Try to do that. Um, let's see, if we want to do a lift coefficient. CL lift over half rho squared times need some reference area. So let's let the reference area be the cross section of the, I think it's the base, probably. Y squared, assuming we have a non-zero base. So let's assume we have a pointy nose and not a pointy tail. If we shove in our equation for the left, that would be this stuff. And all you get left is 2 times alpha, which is ridiculously simple. I have not thought about doing homework for this just because the CFX would be tedious in 3D, and we'll start to get into some of the things that come up, but talking about like a body of revolution at an angle of attack, I might look at this a little bit more, but that cross section, we are using potential flow for it. Some cylinder that's moving down, and we're getting our lift force out of that, which is a little weird because now we're getting a force that's in the direction against the stream, which said we shouldn't get. The added mass portion lets us get something meaningful out of that. What else happens when flow goes over a cylinder, assuming that it's like this 2D slice? What was the that was the problem with potential flow, right? Is it assumed that the flow came right around and joined up and we got zero drag out of it. What really happens is we get this current vortex stream. And so if we tried to do this in 3D and CFX, the problem is that you can actually get these. And a lot of times in CFX, when we have multidimensional, three-dimensional problems, we'd like to cut it in half, and when we do half of it, save time. But when you do that, this loop wake is asymmetric. But as soon as I cut it in half and apply a symmetry plane, I've excluded the possibility of asymmetry. And it turns out that kind of corrupts the whole, the shedding phenomenon is totally different. Anyways, if you wanted to do this in ZFX, it would inherently become an unsteady problem, and it would just be super expensive and hard. So I can't find an easy way to do this in CFX. I don't know how far you can take it. All right. Let's go ahead and stop there for the day. Keep plugging away on homework 5. I'll get 6 posted here soon. That's going to be a wave rider problem. So it'll be 3D, but we try to keep it manageable, so it's treated as inviscid as we can. And yeah, it's usually pretty fun problems. All right. See you guys Thursday.